In this video, we are going to be looking at how we can use truth tables in discrete math. So where do we use truth tables? Let's say we had something like this, where we have a left-hand side and a right-hand side, and it's a question that asks us to prove if these two expressions are congruent. Is the left side congruent to my right side? So a method for this is to use a truth table. So before we do an entire logical equivalence using a truth table, it is important to understand the individual logical operators and their truth tables. So we'll start with these three over here. So the very first one that we're going to be looking at is the truth table for negation, which is basically not P. And I guess the word that goes with not P is not, or I guess a term, right? So how does this work? We have one single letter here, which is P, and it can either be true or false, right? And when we invert it, which is basically what the negation is doing, it's going to go from true to false. And if I have false at the beginning, it's going to go to true. So that's all for the negation. It's fairly simple. Now let's go to the conjunction. Now the conjunction involves two letters here. We have P and we have Q, right? Another important thing to note about the conjunction is that it represents and. So let's look at it. Our P is going to be set up like this. We're going to have true, true, false, false, and our Q is going to be set up with true, false, true, false. This is so we can get all the possibilities. So for conjunction, both have to be true in order for the output to be true. So P has to be true and Q has to be true in order for their P and Q to be true. So let's go through it. So if I have true and true, it'll be true. If it's true and false, it'll be false. And if it's false and true, it'll be false. And if it's false and false, it'll be false. Now, for the third one here, we have a disjunction. It is also known as an OR. So again, we have the same setup here with true, true, false, false for P, and Q with true, false, true, false. Now, for OR, it works in an interesting way. Just one of them has to be true in order for our output to be true. So in this case, we have P true and Q is true, so our output will be guaranteed to be true. If P is true and Q is false, then we're going to get true as well. If P is false and Q is true, we'll get true. The only case here where it doesn't work, where we're not going to get true, is when we get false and false, right? Because one of them is not true. So therefore, when we have false and false, we will get a false when we're looking at the OR, also known as the disjunction. Okay, so our next one that we're going to be looking at is the conditional. So basically an implication. So again, we're using the same setup with our P being T, TFF, while our Q's being TF, TF. So our implication is a little interesting. If we have true and true, we'll get true. And if we have true implying false, we'll have false. If we have false implying true, we'll have true. And then if we have a false that's implying a false, we'll have a true. I guess this one is a little bit tricky because I guess it's something that we can't imagine in our head really well. But over time, practicing it, it will be better. The next one here we have is the biconditional. So again, the setup is the same for our P and Q. So again, P, biconditional, I guess I'll just call it biconditional, if and only if. It's hard to say what it is, right? So it's P, biconditional Q, you'll get true, right? If we have true and true, we will get true. If we have true and false, we'll get false, false and true, false, false and false, true. And this is all in regards to the biconditional. I guess another one that may be tricky to understand or memorize, right? I guess a key idea here would be that if you have your P and Q to be the same thing, then your output for the biconditional would be the true, right? Here if you have false and false, you have true, right? But if your P and Q are different, let's say P is false and Q is true, then you'll have a false. And if your P is true and your Q is false, you'll have a false. Our last one that we're going to be looking at is the exclusive OR. And for that, we have the same setup with our P and Q. And the output, I guess the exclusive OR does actually have a pattern. If I have P true and Q true, then the exclusive OR P and Q would be false, right? And if they're different, it'll be true. So if P is true and Q is false, then we have true. If P is false and Q is true, we'll have true, right? So in a way, it's the opposite of the biconditional. It's the opposite of the biconditional, because if the P and Q are the same thing, then we'll get false. If P and Q, again, the same thing, we'll get false. But if they're different, we'll get true. So now let's do an actual question. So on the left side, we have not P and Q. I guess a not is in front of it. And on the right side, we have not P or not Q. And I'm saying that these two are congruent. And we're going to use this truth table to help us figure this out. Okay. Now you may be asking, why is everything broken up into pieces? I have a P here, I have a Q here. Not P, not Q, P and Q, not P and Q, and finally, not P or not Q. Now, you guys may have seen that this one is this one is this one. What are these? So basically the way we're doing this is we're kind of breaking apart the problem and building back up, right? Until we get to the final things that we need, and we're going to compare these two. All right, so let's actually do it. So again, we've built our stuff here with the regular stuff that we do, how we're building it with true, true, false, false, and false, true, false, false, true, false, true, false, true. And so let's use the knowledge that we've built to do this. So let's say our P is true, then not P, remember we invert it, so it'll be false. And let's say our P was true, then of course we'll have false again. And let's say our P is false, then our not P is going to be true. And let's say our P is false, we're going to have true again. Okay? Now let's look at not Q. Not Q would just be flipping Q. So if my Q's first one was false, then this will be true. And if the first one for Q is true, it'll be false here. And if the third one is false, then it'll be true here. And let's say the fourth one is true, then this will be false. We're just flipping it. I'll say the fourth one, now it's asking for P and Q. So now we're going to use the AND operator that we talked about. So we'll say P is true and Q is false. So they both have to be true in order for our output to be true. So in this case, if we have true and false, we're going to have false. We're comparing these two. Right? So let's say we had true and true. True and true, we're going to have true. Let's say we had false and false, is false. And if we have false and true, we're going to have false. Now, the next thing we're going to be looking at, the next segment, is actually what we need. So we're almost there. So again, we are taking the negation of P and Q. So all we're doing is going to be flipping each one of these. Okay? So this false is going to become true. This true is going to become false. This false is going to become true. This false is going to become true. Okay? So now we've done our left-hand side. This is our left-hand side. And our right-hand side is not P or not Q. So what are we going to compare? What are we comparing? We're comparing not P and not Q, and we're going to be using or in between them. So if I have false or true, I'm going to get true. And if I have false or false, I'm going to get false. If I have true or true, I'm going to get true. And true or false, I'm going to get true. So let's compare our final two, I guess, group of trues and falses. So here and here, we said look at these two. And are they matching? Yes, they are. True on both sides, false on both sides, true on both sides, true on both sides. Now, since in our truth table, these two are the same, right? This means that these two expressions are congruent. So that's it to this video. Hope it helped.